One, two. All right, cool. So back here, training set and validation set versus test set. This article teaches the importance of splitting a data set into training, validation, and test sets. Testing our model. Supervised machine learning algorithms are amazing tools capable of making predictions and classifications. However, it is important to ask yourself how accurate those predictions are. After all, it's possible that every prediction your classifier makes is actually wrong. Luckily, we can leverage the fact that supervised machine learning algorithms, by definition, have a data set of pre-labeled data points. In order to test the effectiveness of your algorithm, we'll split this data into training set, validation set, test set. Training set versus validation set. The training set is the data that the algorithm will learn from. Learning looks different depending on which algorithm you are using. For example, when using linear regression, the points in the training set are used to draw the line of best fit. In k-nearest neighbors, the points in the training set are the points that could be the neighbors. After training using the training set, the points in the validation set are used to compute the accuracy or error of the classifier. The key insight here is that we know the true labels of every point in the validation set, but we're temporarily going to pretend like we don't. We can use every point in the validation set as input to our classifier. We'll then receive a classification for that point. We can now peek at the true label of the validation point and see whether we got it right or not. If we do this for every point in the validation set, we can compute the validation error. Validation error might not be the only metric we're interested in. A better way of judging the effectiveness of a machine learning algorithm is to compute its precision, recall, and F1 score. How to split. Figuring out how much of your data should be split into your validation set is a tricky question. If your training set is too small, then your algorithm might not have enough data to effectively learn. On the other hand, if your validation set is too small, then your accuracy, precision, recall, and F1 score can have a large variance. You might happen to get a really lucky or a really unlucky split. In general, putting 80% of your data in the training set and 20% of your data in the validation set is a good place to start. N-fold cross-validation. Sometimes your data set is so small that splitting it 80-20 will still result in a large amount of variance. One solution to this is to perform n-fold cross-validation. The central idea here is that we're going to do this entire process n times and average the accuracy. For example, in 10-fold cross-validation, we'll make the validation set the first 10% of the data and calculate accuracy, precision, recall, and F1 score. Then we'll make the validation set the second 10% of the data and calculate these statistics again. We can do this process 10 times, and every time the validation set will be a different chunk of the data. If we then arrange all of the accuracies, we'll have a better sense of how our model does on average. Changing the model or test set. Understanding the accuracy of your model is invaluable because you can begin to tune the parameters of your model to increase its performance. For example, in the k-nearest neighbors algorithm, you can watch what happens to accuracy as you increase or decrease k. You can try out all of this in our k-nearest neighbors lesson. Once you're happy with your model's performance, it is time to introduce the test set. This is part of your data that you partitioned away at the very start of your experiment. It's meant to be a substitute for the data in the real world that you're actually interested in classifying. It functions very similarly to the validation set, except you never touch this data while building or tuning your model. By finding the accuracy, precision, recall, and F1 score on the test set, you get a good understanding of how well your algorithm will do in the real world. Introduction to multiple linear regression. Linear regression is useful when we want to predict the values of a variable from its relationship with other variables. There are two different types of linear regression models: simple linear regression and multiple linear regression. In predicting the price of a home, one factor to consider is the size of the home. The relationship between those two variables, price and size, is important, but there are other variables that factor into pricing a home: location, air quality, demographics, parking, and more. When making predictions for price, our dependent variable will want to use multiple independent variables. To do this, we'll use multiple linear regression. Multiple linear regression uses two or more independent variables to predict the values of the dependent variable. It is based on the following equation that we'll explore later on: y equals b plus m1x1 plus m2x2 plus and so on till mn(xn). Street easy data set. You'll learn multiple linear regression by performing it on this data set. It contains information about apartments in New York. Before we start digging into the street easy data, add this line at the end of script.py. and then press run to see the graph. In this example, we used size in square feet and building age in years as independent variables to predict the rent. When we have two independent variables, we can create a linear regression plane. We can now guess what the rent is by plugging in the independent variables and finding where they lie on the plane. StreetEasy dataset. StreetEasy is New York City's leading real estate marketplace, from studios to high-rises, Brooklyn Heights to Harlem. In this lesson, you will be working with a dataset that contains a sample of 5,000 rentals listings in Manhattan, Brooklyn, and Queens, active on StreetEasy in June 2016. It has the following columns. Rental IDs, the rental ID. Rent is the price of rent, so bedrooms, bathrooms, size, square foot, minutes to subway, floor, building age and years, no fee, has roof deck, has washer dryer, has doorman, has elevator, has dishwasher, has patio, has gym, neighborhood, borough. For some more information can be found there. Let's start by doing exploratory data analysis to understand the dataset better. We have broken the dataset for you into Manhattan.csv, Brooklyn.csv, Queens.csv. First, pick a borough out of the three that you are most interested in. We're going to import the dataset and store it in a variable called df. To import, we will need to run this snippet, pd.read csv, and I'll do Manhattan.csv. Replace path with one of the three rows above. Did I type a B? Does it need to be double quotes? What is happening? Is Codecademy down right now or something? Why is it trying to play games with me? I don't understand. Like, why make that obscure? Why? Just why? Whatever. For example, if you want to take a look at the Manhattan data, let's replace the path with one of the three rows above. Okay. Each data set is going to be very different from the others. In this lesson, you're going to pick one of them. Now we have a data frame named df. A data frame is a two-dimensional labeled data structure with columns of potentially different types. You can think of it like a spreadsheet or an SQL table. It is generally the most commonly used pandas object. Let's take a look at the first few rows using df.head. How far is the apartment? Oh. Thinking I'm in a Jupyter notebook or something. So how far is the apartment in the third row from a subway station? 2 minutes. Which neighborhood is it in? Midtown. Training set versus test set. As with most machine learning algorithms, we have to split our data set into a training set, the data used to fit the model, and a test set, the data partitioned away at the very start of the experiment to provide an unbiased evaluation of the model. So training set and our test set, in general, putting 80% of your data in the training set and 20% of your data in the test set is a good place to start. Suppose you have some values in X and some values in Y. From sklearn.model selection, import train test split. So xtrain, xtest, ytrain, ytest equals train test split. And then the parameters, the x value, the y value, the train size, and the test size. Here are the parameters: the train size, the proportion of the data set to include in the train split; test size, proportion of the data set to include in the test split; random state, the seed used by the random number generator, and it's optional. Import train test split from sklearn.model selection. create a data frame X that selects the following columns from the main df data frame. So I don't know why it's skipping steps here, but didn't really tell me how to do that. So to select the columns from the data frame, X equals df so all of that. So these are our goodness. So all of that in X is our dependent variables, sorry, our independent variables, and Y, the rent, is our dependent variable. Use SciKit learn's train test split method to split X into 80% training set and 20% testing set and generate X train, X test, Y train, Y test, set the random state to 6. So X train, X test, Y train, Y test, X train, test, split, X, Y, train size, 0.8, test size, 0.2, random state equals 6, I believe. Let's take a look at the shapes of X train, X test, Y train, and Y test to see we got the proportion we wanted. We have 14 features that we're looking for each apartment and 1 label we're looking for each apartment. So print X train, the shape attribute for NumPy arrays returns the dimensions of the array. If array has n rows times m columns, then array.shape returns nm. So xtrain.shape goodness. Xtrain.shape, X test.shape, Y train, and Y test. So Manhattan looking good. So it has this many rows and this many columns, this many rows, this many columns, this many rows, this many columns, this many rows, this many columns. Cool. Multiple linear regression, SciKit learn. Now we have the training set and the test set. Let's use SciKit learn to build the linear regression model. The steps for multiple linear regression in SciKit learn are identical to the steps for simple linear regression. Just like simple linear regression, we need to import linear regression from the linear model module. So from sklearn.model selection, we imported train test split, but we need from sklearn.linear model import linear regression, then create a linear regression model. So, and then fit it to your X train and Y train data. So create a linear regression model and call it MLR. Fit the model using X train and Y train. So MLR equals linear regression and MLR.fit X train to the Y train. Finds the coefficients in the intercept value. Use the model to predict Y values from X test. Store the predictions in a variable called yPredict. So yPredict equals MLR.predict. So use the model to predict Y values from X test. Store the values in a variable called. Now we have X test, X train, Y train, and yPredict. So yPredicted equals MLR.predict X test. Yeah. To see this model in action, let's test it on Sunny's apartment in Greenpoint, Brooklyn. Or if you reside in New York, plug in your own apartment's values and see if you are over or underpaying. So talking about? This is a 1-bedroom, 1-bath apartment that is 620 square feet. Did it already set up? Why is it skipping steps? It's being weird. Oh, street easy equals pd.read. Okay. Sunny doesn't have an elevator, so the 11th item in the list is that. So Sunny's apartment equals that. Predict equals. I don't know why this feels weird. I don't know why it's doing this, but print predicted rent and this formatting. Anyway, this is weird. So he's underpaying. Visualizing results with matplotlib. You've performed multiple linear regression. And you also have the predictions in ypredict. However, we don't have insight into the data yet. In this exercise, you'll create a 2D scatter plot to see how the independent variables impact prices. How do you create 2D graphs? Graphs can be created using matplotlib's pyplot module. Here's the code with inline comments explaining how to plot using matplotlib's .scatter. So create a scatter plot, plot.scatter x, y, alpha 0.4, create x-axis label and y-axis label, plot.x label, the x-axis label, and plot.y label, the y-axis label. Create a title, plot.title is title, show the plot, plot.show. We want to create a scatter plot like this. Create a 2D scatter plot using ytest and ypredict. So add appropriate x labels and y-axis labels. So I guess the x labels would be apartment info, y-axis label would be rent. I guess this should be apartment plot. Show the plot using plot.show. Using our info, this is our rent predictions. What's the predicted prices versus the actual prices? I see. Multiple linear regression equation. Now that we have implemented multiple linear regression, we'll learn how to tune and evaluate the model. Before we do that, however, it's essential to learn the equation behind it. The equation 6.1. So the equation for multiple linear regression that uses two independent variables is this: y equals b plus m1 x1 plus m2 x2. Equation for so it's just y equals mx plus b, but with more mx's for the amount of independent variables. Here, m1, m2, m3, mn refer to the coefficients, and b refers to the intercept that you want to find. You can plug these values back into the equation to compute the predicted y values. Remember, with sklearn's linear regression method, we can get these values with ease. The .fit method gives the model two variables that are useful to us: .coef underscore, which contains the coefficients, and .intercept underscore, which contains the intercept. After performing multiple linear regression, you can print the coefficients using .coef underscore. Coefficients are most helpful in determining which independent variable carries more weight. For example, a coefficient of -1.345 will impact the rent more than a coefficient of 0.238, with former impacting prices negatively and latter positively. Print out the coefficients using .coef. So mlr .coef, and we're going to print it. coefficients, so you can see clearly, it looks like bathrooms matters significantly, if I'm reading this right. Bathrooms is the most important trait. After that, it's followed by bedrooms. And what matters the least is the size in square feet. This is interesting. So correlations in our Manhattan model, we use 14 variables, so there are 14 coefficients. To see if there are any features that don't affect price linearly, let's graph the different features against rent. Interpreting graphs, in regression, the independent variables will either have a positive linear relationship to the dependent variable, a negative linear relationship, or no relationship. A negative linear relationship means that as x values increase, y values will decrease. Similarly, a positive linear relationship means that as x values increase, y values will also increase. Graphically, when you see a downward trend, it means a negative linear relationship exists. When you find an upward trend, it indicates a positive linear relationship. Cool. Create a scatter plot of size, square feet, and rent. So plot.scatter df size, square feet, df rent, alpha equals 0.4. So this is the size in square feet, and this is the rent. So clearly, the bigger the size in square feet, the rent goes up, but only to a point, really. There's a diminishing return after about 3,000. Let's create a scatter plot of min to subway and rent. So plot.scatter df min to subway df rent alpha 0.4. Is there a strong correlation? No. No, there is not. So regardless of, well, I guess actually it's hard to see, right? Because this, here, maybe we should try doing it like that. Okay, so there's I wouldn't say necessarily a strong correlation, no. Do the same for a few others and write down the ones that don't have strong correlations. So let's try bathrooms. So it's categorical, right, which makes sense. There's a correlation there, though. It's pretty linear. Well, I guess not necessarily. It's, I mean, linear. I guess that's one way to describe it. If I say bedrooms, okay. Yeah, there's a correlation there for sure, but it's kind of a drop off. Diminishing returns after 3, really. Evaluating the model's accuracy. When trying to evaluate the accuracy of our multiple linear regression model, one technique we can use is residual analysis. The difference between the actual value y and the predicted value y hat is the residual e. The equation is e equals y minus y hat. In the StreetEasy dataset, y is the actual rent, and the y hat is the predicted rent. The real y values should be pretty close to these predicted y values. sklearn's linear model.linear regression comes with a .score method that returns the coefficient of determination r squared of the prediction. The coefficient r squared is defined as 1 minus u over v, where u is the residual sum of squares, y minus y predict squared dot sum, and v is the total sum of squares, y minus y dot mean squared dot sum. The TSS, the total sum of squares, tells you how much variation there is in the y variable. R squared is the percentage variation in y explained by all the x variables together. For example, say we are trying to predict rent based on the size square foot in the bedrooms in the apartment, and the r squared for our model is 0.72. That means that all the x variables, square feet, and number of bedrooms together explain 72% variation in Y rent. Now let's say we add another x variable, building's age, to our model. By adding this third relevant x variable, the r squared is expected to go up. Let's say the new r squared is 0.95. This means that square feet, number of bedrooms, and age of the building together explain 95% of the variation in the rent. The best possible r squared is 1, and it can be negative because the model can be arbitrarily worse. Usually a r squared of 0.7 is considered good. Use the score method from linear regression to find the coefficient of determination, r squared, for the training set. Write that number down. So is that right? Use the score method from linear regression to find the coefficient of determination for the testing set. It wants me to write it down, so what is happening? Hold on. Copied them. Put those there. So on to the next. Rebuild the model. Now let's rebuild the model using the new features, as well as evaluate the new model to see if we improved. For Manhattan, so why did I have to write them down? Whatever. Print the coefficients again to see which ones are strongest. Something about this, I feel like they put a lot of work into those, the animations at the beginning, but they put less work into this. So, like usually it tells you where's the right place to put it. So I guess should be fine if I do it here. So print. Like instead of writing that down, I should have just written down the last thing. I'm just gonna go back and copy it. This is annoying. So MLR isn't defined because in here it's called LM. For some reason they changed the names on me. Where did I paste that? Oh, they already had it? Oh, man. Currently the X should look something like that. Remove some of the features that don't have strong correlations and see if your score improved. So I'm gonna guess has dishwasher, doesn't really matter much. No fee, I'm guessing doesn't really matter much. Floor, I'm guessing doesn't really matter much. Has doorman, I'm guessing doesn't really matter much. Let's see if things go up. Went down actually. What if I get rid of interesting, it's not going up. It's going down. Great work. Let's review the concepts before you move on. Multiple linear regression. This is just an ad for Street Easy. That's what this is turned into. Great work. Let's review the concepts before you move on. Multiple linear regression uses two or more variables to make predictions about another variable. Multiple linear regression uses a set of independent variables and a dependent variable. It uses these variables to learn how to find optimal parameters. It takes a labeled data set and learns from it. Once we confirm that it's learned correctly, we can then use it to make predictions by plugging in new x values. We can use SciKit learns linear regression to perform multiple linear regression. Residual analysis is used to evaluate the regression model's accuracy. In other words, it's used to see if the model has learned the coefficients correctly. SciKit learns linear model.linear regression comes with a .score method that returns the coefficient of determination r squared of the prediction. The best score is 1.0. We've made an applet using the multiple linear regression model that you built. Have fun. It's not fun. Find the error. Which line would break the following code? So from sklearn.linear model, import linear regression, xtrain, ytrain, xtest, ytest, regra equals linear regression, ypredict equals regra.predict, xtest, regra.fit, xtrain, ytrain. So this would break it because you can't predict it before you fit it. Which of the two coefficients will have a greater impact on the dependent variable? Coefficient of negative 1.5 or coefficient of 1.5 will have the same level of impact. Great work. One will cause y values to drop and the other will cause them to rise. However, they'll do it with the same level of impact. Which of the following statements is true about residual analysis? Residual analysis allows you to assess the accuracy of a classification model. Residual analysis allows you to assess the accuracy of a multiple linear regression model. A residual is the difference between the training set and the test set. I'm not 100% sure actually. I'm going to guess this though because that's what we were just learning. Yep, this is accurate. And a residual is the difference between the real value and the predicted value. Okay. I like how it reminds us just because it was not that clear about that. Given a regression line and 4 data points, which point has the largest residual? So this is our regression line. These are our data points. So it appears that C has the largest residual. Correct, it has the greatest difference between the observed value of the dependent variable y and the predicted value y hat. In the multiple linear regression equation, what are the m variables? The coefficients. Correct, the coefficients are helpful in determining which independent variable carries more weight. True, false. The test set is the data that you partition away at the very start of your experiment to provide an unbiased evaluation of the model. That's true. Fill in the blank. What is the module we are importing from? From sklearn.linear model, import linear regression. What does it mean for a model to have an r-squared value of 0? A value of 0 would indicate that the model fails to accurately predict the data at all. Value of 0 would indicate the model is a perfect fit. Correct, value of 0 would indicate the model fails to accurately model the data at all. What is a portfolio project? This project is a little different from other Codecademy projects you've encountered. In this project, you will bring together what you've learned in previous lessons to build a project in your own development environment and publish it to the web. Create your own files outside the Codecademy platform. Write your own code with less guided instructions. Use common project management processes to track your progress. How do they work? We'll provide you with high-level tasks to guide your project to completion, but you'll be responsible for deciding how to implement them in your code. There are many possible ways to correctly fulfill all these requirements. You should expect to use the internet, Codecademy, and other resources when you encounter a problem you cannot easily solve. Note that there are hints that can assist you, but they will only provide one potential implementation. Do not worry if your program looks different than ours. So this is a regression cumulative project. Use your knowledge of supervised machine learning models for regression to predict the rating of a restaurant, which I'm not going to do this because I just want to learn more. So supervised learning classification. So left over in the curriculum is classification with k nearest neighbors, logistic regression and decision trees. Then there's advanced classification with evaluation metrics, support vector machines, naive Bayes classifier, and then another project, and then we go to unsupervised learning with clustering, and then neural networks. Okay, cool. So let's do k nearest neighbors. K-nearest neighbors classifier. K-nearest neighbors KNN is a classification algorithm. The central idea is that data points with similar attributes tend to fall into similar categories. Consider the image to the right. This image is complicated, but for now, let's just focus on where the data points are being placed. Every data point, whether its color is red, green, or white, has an X value and a Y value. As a result, it can be plotted on this two-dimensional graph. Next, let's consider the color of the data. The color represents the class that the K-nearest neighbor algorithm is trying to classify. In this image, data points can either have the class green or the class red. If a data point is white, this means that it doesn't have a class yet. The purpose of the algorithm is to classify these unknown points. Finally, consider the expanding circle around the white point. This circle is finding the K nearest neighbors to the white point. When K equals 3, the circle is fairly small. 2 of the 3 nearest neighbors are green and 1 is red. So in this case, the algorithm would classify the white point as green. However, when we increase K to 5, the circle expands and the classification range changes. 3 of the nearest neighbors are red and 2 are green, so now the white point will be classified as red. This is the central idea behind the K nearest neighbor algorithm. If you have a data set of points where the class of each point is known, you can take a new point with an unknown class and find its nearest neighbors and classify it. Before moving on to the next exercise, consider the image below. If K equals 1, what would the class of the question mark be? It would be a triangle. If K equals 5, what would it be? So 1, 2, 3, 4. I'd say probably a square, right? 1, 2, 3, 4, 5. Note that rather than using colors in this image, the class is denoted by the shape of each point. Introduction. Before diving into the K nearest neighbors algorithm, let's first take a minute to think about an example. Consider a data set of movies. Let's brainstorm some features of a movie data point. A feature is a piece of information associated with a data point. Here are some potential features of movie data points: the length of the movie in minutes, the budget of a movie in dollars. If you think back to the previous exercise, you could imagine movies being places in that two-dimensional space based on those numeric features. There could also be some Boolean features, features that are either true or false. For example, here are some potential Boolean features. Black and white. This feature would be true for black and white movies and false otherwise. Directed by Stanley Kubrick. This feature would be false for almost every movie, but for the few movies that were directed by Kubrick, it would be true. Finally, let's think about how we might want to classify a movie. For the rest of this lesson, we're going to be classifying movies as either good or bad. In our data set, we've classified a movie as good if it had an IMDb rating of 7.0 or greater. Every good movie will have a class of 1, while every bad movie will have a class of 0. To the right, we've created some movie data points where the first item in the list is the length, the second is the budget, and the third is whether the movie was directed by Stanley Kubrick. Add another movie to the code to your right, add the variable Gone with the Wind. So this movie is 2:38 minutes long, had a budget of $3,977, and it was not directed by Stanley Kubrick. Gone with the Wind. Distance between points, 2D. In the first exercise, we were able to visualize the data set and estimate the K nearest neighbors of an unknown point, but a computer isn't going to be able to do that. We need to define what it means for 2 points to be close together or far apart. To do this, we're going to use the distance formula. For this example, the data has 2 dimensions: the length of the movie, the movie's release date. Consider Star Wars and Raiders of the Lost Ark. Star Wars is 125 minutes long and was released in 1977. Raiders of the Lost Ark is 115 minutes long and was released in 1981. The distance between the movies is computed below. Write a function named distance that takes 2 lists named movie 1, movie 2 as parameters. You can assume that each of these lists contains 2 numbers, the first number being the movie's runtime and the second number being the year the movie was released. The function should return the distance between the 2 points. Remember, in Python, x to the power of 0.5 will give you the square root of x. Similarly, x to the power of 2 will give you the square of x. So we have this function distance movies. You can assume a list containing 2 numbers. So and we're are expecting integer. So write a functioning distance that takes, and we're going to return the distance between the two lists. So for I in range, length of movie 1, distance takes two lists, name movie 1 and movie 2 as parameters. You can assume that each of these lists contains two numbers, the first number being the movie's runtime and the second number being the year the movie was released. The function should return the distance between the two lists. So for I in range, length of movies, distance plus equals and we're going to get the square root. So distance plus equals movie 1 I minus movie 2 I squared, initialize distance 0. Name list is not defined. Oh, this is using Python 3. It's weird. Call the function on some of the movies we've given you. Start Wars. Names. Print the distance between Star Wars and Raiders of the Lost Ark. Print the distance between Star Wars and Mean Girls. Which movie is Star Wars more similar to? Definitely Raiders of the Lost Ark. Distance between points 3D. Making a movie rating predictor based on just the length and release date of movies is pretty limited. There are so many more interesting pieces of data about movies that we could use, so let's add another dimension. Let's say this third dimension is the movie's budget. We now have to find the distance between these 2 points in 3 dimensions. What if we're not happy with just 3 dimensions? Unfortunately, it becomes pretty difficult to visualize points in dimensions higher than 3, but that doesn't mean we can't find the distance between them. The generalized distance formula between points A and B is as follows. Here, A1, B1 is the difference between the first feature of each point. AN minus BN is the difference between the last feature of each point. Using this formula, we can find the k nearest neighbors of a point in n-dimensional space. We now can use as much information about our movies as we want. We will eventually use these distances to find the nearest neighbors to an unlabeled point. Modify your distance function to work with any number of dimensions. It already did. Trying to total distance between the 2 movies. We've added a third dimension to each of our movies. Print the new distance. Goodness. Which movie's closer to Star Wars now? Looking like Mean Girls. Data with different scales, normalization. In the next 3 lessons, we'll implement the 3 steps of the k nearest neighbor algorithm. Normalize the data, find the k nearest neighbors, classify the new point based on those neighbors. When we added the dimension of budget, you might have realized there are some problems with the way our data currently looks. Consider the 2 dimensions of release date and budget. The maximum difference between two movies' release dates is about 125 years. The Lumiere brothers were making movies in the 1890s. However, the difference between two movies' budget can be millions of dollars. The problem is that the distance formula treats all dimensions equally, regardless of their scale. If two movies came out 7 years apart, that should be a pretty big deal. However, right now that's exactly equivalent to two movies that have a difference in budget of $70. The difference in 1 year is exactly equal to the difference in $1 of budget. That's absurd. Another way of thinking about this is that the budget completely outweighs the importance of all the other dimensions because it is on such a huge scale. The fact that two movies were 7 years apart is essentially meaningless compared to the difference in millions in the other dimension. The solution to this problem is to normalize the data so every value is between 0 and 1. In this lesson, we're going to be using min-max normalization. Write a function named min-max normalize. That takes a list of numbers named LST as a parameter. LST short for list. Whoa. Begin by storing the minimum and maximum values of the list in variables named minimum and maximum. Minimum equals min list or LST. Like, what's the point of getting rid of the I? Just call it list. Did I misspell minimum? No. Maximum equals max LST. Create an empty list named normalized. Loop through each value in the original list. So for I, slut, LST. For I in range length, LST. Using min-max normalization, normalize the value and add the normalized value to the new list. So I hate that they didn't teach us how to do min-max normalization manually. But let me try to figure it out. So minimum equals the minimum of the list, right? So what is it, 1897? That's the minimum. So I guess you could, for I in range length of list, normalized dot append LST I How would you do this? I don't know how to do it. Value minus minimum divided by maximum minus minimum. Okay, so LST I minus minimum divided by maximum minus minimum. After adding every normalized value to normalize, return normalized. What did I do wrong? Return normalized. Invalid syntax. Oh. Call the min-max normalize using the given list release dates. So print the resulting list. What does the date 1897 get normalized to? Why is it closer to 0 than 1? Okay, so actually the minimum value was 91, not 97. Finding the nearest neighbors, the k nearest neighbor algorithm. Normalize the data. Now we're on to find the k nearest neighbors. So, and then after that, we'll classify the new point based on those neighbors. Now that our data has been normalized and we know how to find the distance between 2 points, we can begin classifying unknown data. To do this, we want to find the k nearest neighbors of the unclassified point. In a few exercises, we'll learn how to properly choose k, but for now, let's choose a number that seems somewhat reasonable. Let's choose 5. In order to find the 5 nearest neighbors, we need to compare this new unclassified movie to every other movie in the data set. This means we're going to be using the distance formula again and again. We ultimately want to end up with a sorted list of distances and the movies associated with those distances. It might look something like this. A list with first list is 0.3, Superman 2. Next one is 0.31, Finding Nemo, on until 0.38, Blazing Saddles. In this example, the unknown movie has a distance of 0.30 to Superman 2. In the next exercise, we'll use the labels associated with these movies to classify the unlabeled point. Begin by running the program. We've imported and normalized a movie dataset for you and printed the data for the movie Bruce Almighty. Each movie in the dataset has three features: the normalized budget in dollars, the normalized duration in minutes, and the normalized release year. We've also imported the labels associated with every movie in the dataset. So for movies, import movie dataset, movie labels, print movie dataset, Bruce Almighty, print movie labels, Bruce Almighty, which is nothing right now, it's 0. The label associated with Bruce Almighty is a 0, indicating that it is a bad movie. That's wrong. Remember, a bad movie had a rating less than 7.0 on IMDb. Comment out the two print lines after you have run the program. Create a function called classify. It has three parameters: the data point you want to classify named unknown, the dataset you are using to classify it named dataset, and k, the number of neighbors you're interested in. For now, put pass inside the function. Inside the classify function, remove pass. Create an empty list called distances. Loop through every title in the dataset. So for title dataset, access the data associated with every title by using dataset title. Find the distance between dataset title and unknown. So dataset title minus unknown. Distance equals dataset title minus dataset unknown squared. And store this value in a variable named distance to point. Add the list distance to point title to distances. Outside the loop, return distances. Unsupport operand types. What'd I do? For title in dataset. You should loop through every point in the dataset using for title in dataset. Find the distance between each point and unknown using pi distance. Oh, I forgot I had this function. Totally forgot. Set append distance to point title. Cool. We now have a list of distances and points. We want to sort this list by the distance from smallest to largest. For returning distances, use Python's built-in sort function to sort distances. The k nearest neighbors are now the first k items in distances. Create a new variable named neighbors and set it equal to the first neighbors. Set the first k items of distances. Use Python's built-in slice function. Okay. Oh, I forgot to return neighbors. Test the classify function and print the results. Point. Take a look at the 5 nearest neighbors. Lady Vengeance. I haven't seen that, but I've seen what's the movie before it? Oh, what's that movie called? Something Vengeance. It's really good. But anyway, Steamboy, Fateless, Princess Mononoke, Godzilla. So I don't know about Steamboy and Fateless, but I know that Princess Mononoke, Godzilla, and Lady Vengeance are all Asian movies. I mean, Princess Mononoke is Japanese. Godzilla 2000 might be the American version. I'm not sure. But the original Godzilla is Japanese, and Lady Vengeance is a Korean movie. What is that movie called? Something Vengeance. Is it Mr. Vengeance? Hold on. It really doesn't matter. No. Mr. Vengeance? Sympathy for Mr. Vengeance. Trippy movie. Trippy movie. Okay, anyway. Here. So, it says classify function. Alright, cool. We're good. Count neighbors. The k nearest neighbor algorithm. Normalize the data. We did that. Find the k nearest neighbors. We did that. Classify the new point based on those neighbors. We've now found the k nearest neighbors and have stored them in a list that looks like this. Our goal now is to count the number of good movies and bad movies in the list of neighbors. If more of the neighbors were good, then the algorithm will classify the unknown movie as good. Otherwise, it will classify it as bad. In order to find the class of each of the labels, we'll need to look at our movie labels dataset. For example, movie labels Akira will give us 1 because Akira is classified as a good movie. You may be wondering what happens if there's a tie. What if k equals 8? And 4 neighbors were good, 4 neighbors were bad. There are different strategies, but one way to break the tie would be to choose the class of the closest point. Our classify function now needs to have knowledge of the labels. Add a parameter named labels to classify. It should be the 3rd parameter. Continue writing your classify function. Create 2 variables named numGood and numBad. numGood, numBad. Set them each to 0. Store their title in a variable called title. Oh wait, use a for loop to loop through every movie in neighbors. Store their title in a variable called title. So neighbors equals distances 0 through k, and distances so right now neighbors, goodness. So distances 0 through k, and distances is a list of lists where each point is distance to point in the title. So for movie is each of these lists. So title equals movie bracket 1. Remember every neighbor, oh, I could have just read the next line. Every neighbor is a list of distance titles, so the title can be found at index 1. For now, return title at the end of your function outside the loop. Use labels in title to find the label of each movie. If that label is a 0, add 1 to numBad. Use labels in title to find the label of each movie. How I access the labels again? Movie labels. Oh, I see. Titler. Use labels in title to find the label of each movie. If that label is a 0, return num good. Title. We can easily classify our unknown movie. If num good is greater than num bad, return a 1. Otherwise, return a 0. Call classify using the following parameters and print the result. Does the system predict this movie will be good or bad? It says good. Classify your favorite movie. Nice work. Your classifier is now able to predict whether a movie will be good or bad. So far, we've only tested this on a completely random point. In this exercise, we're going to pick a real movie, normalize it, and run it through our classifier to see what it predicts. In the instructions below, we're going to be testing. That's my favorite movie. Okay, I can. Okay, in the instructions below, we're going to be testing our classifier using the 2017 movie Call Me By Your Name. Feel free to pick your favorite movie instead. To begin, we want to make sure the movie that we want to classify isn't already in our database. This is important because we don't want one of the nearest neighbors to be itself. You could do this by using the in keyword. Begin by printing if the title of your movie is in movie dataset. So print, let's do Howl's Moving Castle in movie dataset. True. Let's see. What's my favorite movie? SpongeBob SquarePants movie. Bam. Once you confirm your movie is not in the database, we need to make a data point for your movie. Create a variable named myMovie. And set it equal to a list of 3 numbers. They should be the movie's budget in dollars. I don't want to do all this. I'll pretend it's, no, I'm not going to do that to the movie. Let's see. I'm going to guess SquarePants. I'm going to guess the budget was like 2 mil. Oh, way off. Way off. Crazy. That's $30 million to do that. That's insane. This is actually a way better movie. I'm switching to this Simpsons movie. Yes, sir. It's at 75 mil. That's crazy. But I'm doing that. So back here. This is such a good movie. Man. So my movie, 75 mil. The runtime was, wait, how do I, oh, just get rid of the commas. Runtime, what's it looking like? 2 hours and 7 minutes. So that's 127. And release year, was that like 2007 or something? I think I probably saw it subconsciously. I definitely saw that. So 2007. Next, we want to normalize this data point. We've included the function normalize point, which takes a data point as a parameter and returns the point normalize. Create a variable called normalize my movie. And set it equal to the normalized value of my movie. finally call classify. Yes, sir. Print the result. Did you classify think your movie was good or bad? Chose good. Training and validation sets. You've now built your first k-nearest neighbors algorithm capable of classification. You can feed your program a never-before-seen movie, and it can predict whether its IMDb rating was above or below 7.0. However, we're not done yet. We now need to report how effective our algorithm is. After all, it's possible our predictions are totally wrong. As with most machine learning algorithms, we have split our data into a training set and validation set. Once these sets are created, we will want to use every point in the validation set as input to the k-nearest neighbor algorithm. So again, we have to split our data into training and validation. Once these sets are created, we will want to use every point in the validation set as input to the k-nearest neighbor algorithm. We will take a movie from the validation set, compare it to all the movies in the training set, find the k-nearest neighbors, and make a prediction. After making that prediction, we can then peek at the real answer found in the validation labels to see if our classifier got the answer correct. If we do this for every movie in the validation set, we can count the number of times the classifier got the answer right and the number of the times got it wrong. Using these two numbers, we can compute the validation accuracy. Validation accuracy will change depending on what k we use. In the next exercise, we'll use the validation accuracy to pick the best possible k for our classifier. We've imported training set, training labels, validation set, and validation labels. Let's take a look at one of the movies in validation set. The movie B movies in validation set. Print out the data associated with B movie. Print B movies label as well, which can be found in validation labels. Is B movie a good or bad movie? So how do I print it out? Print validation set B movie. Let's have our classifier predict whether B movie is good or bad using k equals 5. Call the classify function. Store the results in a variable named guess and print guess. So guess equals classify. It's a bad movie. Let's check to see if our classification got it right. If guess is equal to B movie's real class, found in validation labels, print correct. Otherwise, print wrong. You're making me write an if statement for this? How dare you? Correct. Choosing K. In the previous exercise, we found that our classifier got 1 point in the training set correct. Now we can test every point to calculate the validation accuracy. The validation accuracy changes as k changes. The first situation that will be useful to consider is when k is very small. Let's say k equals 1. We would expect the validation accuracy to be fairly low due to overfitting. Overfitting is a concept that will appear almost any time you're writing a machine learning algorithm. Overfitting occurs when you rely too heavily on your training data. You assume that data in the real world will always behave exactly like your training data. In the case of k-nearest neighbors, overfitting happens when you don't consider enough neighbors. A single outlier could drastically determine the label of an unknown point. Consider the image below. The dark blue point in the top left corner of the graph looks like a fairly significant outlier. When k equals 1, all points in that general area will be classified as dark blue, which should probably be classified as green. Our classifier has relied too heavily on the small quirks in the training data. On the other hand, if k is very large, our classifier will suffer from underfitting. Underfitting occurs when your classifier doesn't pay enough attention to the small quirks in the training set. Imagine you have 100 points in your training set. You set k equals 100. Every single unknown point will be classified in the same exact way. The distances between the points don't matter at all. This is an extreme example, however, it demonstrates how the classifier can lose understanding of the training data if k is too big. Begin by creating a function called find validation accuracy. That's 5 parameters: training set, training labels, validation set, validation labels. Okay. Create a variable named numCorrect. Have it begin at 0.0. Loop through the movies validation set. Call classify using each movie's data. The training set. The training labels. And k. Store the result in a variable called guess. What just happened? Guess equals that. For now, return guess outside the loop. Remember, the movie's data can be found by using validation set title. Inside the for loop, compare guess to the corresponding label and validation labels. If they are equal, add 1 to numCorrect. For now, outside the for loop, return numCorrect. Outside the for loop, return the validation error. This should be numCorrect divided by the total number of points in the validation set. What? Outside the for loop, return the way they worded that is strange. So should be numCorrect divided by total number of points in the validation set. Call find validation accuracy with k equals 3 for the results. Print the result of the function with k equals 3. So we need to pass it the arguments. What arguments? Just tell me. Like, just, come on. Stop being obscure. .6639. That's not that great. Graph of k. The graph to the right shows the validation Accuracy of our movie classifier. As k increases, when k is small, overfitting occurs and the accuracy is relatively low. On the other hand, when k gets too large, underfitting occurs and accuracy starts to drop. Seems to be the best k for the data set. It's looking like about 75. Using sklearn, you've now written your own k nearest neighbor classifier from scratch. However, rather than writing your own classifier every time, you can use Python's sklearn library. Sklearn is a Python library specifically used for machine learning. It has an amazing number of features, but for now we're only going to investigate its k nearest neighbor classifier. There are a couple of steps we'll need to go through in order to use the library. First, you need to create a k neighbors classifier object. This object takes one parameter, k. For example, the code below will create a classifier where k equals 3, classifier equals k neighbors classifier, and neighbors equals 3. Next, we'll need to train our classifier. The .fit method takes two parameters. The first is a list of points, and the second is the labels associated with those points. So for our movie example, we might have something like this. Finally, after training the model, we can classify new points. The .predict method takes a list of points that you want to classify, returns a list of guesses for those points. What'd I do wrong? Classifier, k neighbors. Oh. We've also imported some movie data. I think it's fit, right? Yeah. Which movies were classified as good movies? The first two. Which were classified as bad movies? The last one. Remember, those three numbers associated with the movie are the normalized budget, runtime, and year of release. Review. Congratulations, you just implemented your very own classifier from scratch and used Python's sklearn library. In this lesson, you learned some techniques very specific to the k nearest neighbor algorithm, but some general machine learning techniques as well. Some of the major takeaways from this lesson include data with n features can be conceptualized as points lying in n-dimensional space. Data points can be compared by using the distance formula. Data points that are similar will have a smaller distance between them. A point with an unknown class can be classified by finding the k nearest neighbors. To verify the effectiveness of a classifier, data with known classes can be split into a training set and a validation set. Validation error can then be calculated. Classifiers have parameters that can be tuned to increase their effectiveness. In the case of k nearest neighbors, k can be changed. A classifier, data points can be compared using the distance formula. Data points that are similar will have a smaller distance between them. A point with an unknown class can be classified by finding the k nearest neighbors. To verify the effectiveness of a classifier, data with known classes can be split into a training set and a validation set. Validation error can then be calculated. Classifiers have parameters that can be tuned to increase their effectiveness. In the case of k nearest neighbors, k can be changed. A classifier can be trained improperly and suffer from overfitting or underfitting. In the case of k nearest neighbors, a low k often leads to overfitting and a large k often leads to underfitting. Python's sklearn library can be used for many classification and machine learning algorithms. To the right is an interactive visualization of k nearest neighbors. If you move your mouse over the canvas, The location of your mouse will be classified as either blue or green. That's kind of cool. Use the slider. The nearest neighbors to your mouse are highlighted in yellow. Cool. Use the slider to change key to see how the boundaries of the classification change. Pretty cool, pretty cool. So now we're on to regression. Where are we at in the syllabus? So we did k-nearest neighbors. Now we're going to do a regressor. Okay. Regression. The k-nearest neighbors algorithm is a powerful supervised machine learning algorithm typically used for classification. However, it can also perform regression. In this lesson, we will use the movie data set that was used in the k-nearest neighbors classifier lesson. However, instead of classifying a new movie as either good or bad, we are now going to predict its IMDb rating as a real number. This process is almost identical to classification, except for the final step. Once again, we are going to find the k-nearest neighbors of the new movie by using the distance formula. However, instead of counting the number of good and bad neighbors, the regressor averages their IMDb ratings. For example, if the 3 nearest neighbors to an unrated movie have ratings of 5.0, 9.2, and 6.8, then we can predict this new movie will have a rating of 7. We've imported most of the k-nearest neighbor algorithm. Before we dive into finishing the regressor, let's refresh ourselves with the data. At the bottom of your code, print movie data set life of pi. You should see the list of 3 values. These values are the budget, small budget, runtime, relatively short runtime, and the release here, relatively recent. Print the rating for life of pi. This can be found in movie ratings. Name movie ratings 8. We've included the majority of the k-nearest neighbor algorithm in the predict function. Right now, the variable neighbors stores a list of distance title pairs. Loop through every neighbor and find its rating in movie ratings. Add those ratings together and return that sum divided by the total number of neighbors. So variable neighbors stores a list of distance title pairs. So loop through every neighbor. So for neighbors, find its rating in movie ratings. Add those ratings together and return that sum. Okay. This indices must be integers or slices, not string. What did I do wrong? Oh, movie ratings N1. Make sure to divide your sum by the total number of neighbors. Divide the sum. Call predict with the following parameters. So normalized budget runtime and year of the movie Incredibles 2, which I don't think I saw. So the first one was a great movie. The normalized year is larger than 1 because our training set only had movies that were released between 1927 and 2016. Incredibles 2 was released in 2018. Weighted regression. We're off to a good start, but we can be even more clever in the way that we compute the average. We can compute a weighted average based on how close each neighbor is. Let's say we're trying to predict the rating of movie X and we found its 3 nearest neighbors. Consider the following table. So movie A has a rating of 5 and the distance to movie X is 3.2. Movie B has a rating of 6.8 and its distance to movie X is 11.5. Movie C has a rating of 9 and its distance to movie X is 1.1. If we find the mean, the predicted rating for X would be 6.93. However, movie X is most similar to movie C, so movie C's rating should be more important when computing the average. Using a weighted average, we can find movie X's rating. So 5.0 divided by 3.2 plus 6.8 divided by 11.5 plus 9.0 divided by 1.1 all over 1 divided by 3.2 plus 1 divided by 11.5 plus 1 divided by 1.1 equals 7.9. The numerator is the sum of every rating divided by their respective distances. The denominator is the sum of 1 over every distance. Even though the ratings are the same as before, the weighted average has now gone up to 7.9. Let's redo our predict function so it computes the weighted average. Before you begin looping through neighbors, create a variable named numerator and set it equal to 0. Loop through every neighbor. And add the neighbor's rating, find the movie ratings, divided by the neighbor's distance numerator. Neighbor's distance to numerator. Unhashable type list. So let's think about this. Movie ratings, if you just pass the title of it. So let's now calculate the denominator of the weighted average. Before your loop, create a variable named denominator. Set equal to 0 inside your for loop. Add 1 divided by the neighbor's distance to the denominator. Outside the loop, return numerator divided by denominator. Once again, call your predict function. How to, using a weighted average, change the predicted rating. Remember, before calculating the weighted average, so it actually dropped it. SciKit Learn. Now that you've written your own k-nearest neighbors regression model, let's take a look at SciKit Learn's implementation. The k-neighbors regressor class is very similar to k-neighbors classifier. We first need to create the regressor. We can use the parameter n-neighbors to define our value for k. We can also choose whether or not to use a weighted average using the parameter weights. If weights equals uniform, all neighbors will be considered equally in the average. If weights equals distance, then a weighted average is used. So classifier equals k-neighbors regressor, and neighbors equals 3, weights equals distance. Next, we need to fit the model to our training data using the .fit method. .fit takes 2 parameters. The first is a list of points, and the second is a list of values associated with those points. So training points are these 3 lists, and training labels equals these 3 labels. Classifier.fit training points to training labels. Finally, we can make predictions on new data points using the .predict method. .predict takes a list of points and returns a list of predictions for those points. So unknown points are these 3 lists, and guesses equals classifier.predict unknown points. So create a k-neighbors regressor named regressor. where n neighbors equals 5. Distance. We've also imported some movie data. Train your classifier. What I do, regressor.fit, that's what I mean. Let's predict some movie ratings, predict the ratings for the following movies. How dare you think I would type that out? Tab that. These three lists are for Incredibles 2, The Big Stick, The Greatest Showman. Those three numbers associated with the movies are normalized budget. Yeah. Okay, review. Great work. Here are some of the major takeaways from this lesson. The k-nearest neighbors algorithm can be used for regression. Rather than returning a classification, it returns a number. By using a weighted average, data points that are extremely similar to the input point will have more of a say in the final result. SciKit has an implementation of a k-nearest neighbor regressor named k-neighbors regressor. In the browser, you'll find an example of a k-nearest neighbor regressor in action. Instead of the training data coming from IMDb ratings, you can create the training data yourself. Rate the movies that you've seen. Once you've rated more than k movies, a k-nearest neighbor regressor will train on those ratings. It will then make predictions for every movie that you haven't seen. It's pretty cool. I know, great movie, never seen it. Return of the King, I don't really care. Yeah, you get me. Oh yeah, you get me. That's cool. Yeah. Okay. So as you add more and more ratings, all right, cool. Why is normalizing your data essential for k-nearest neighbors so that unusual features are removed? It is not essential so the distance between points positive feature with vastly different scales does not dominate other features. In the following image, k-nearest neighbors will classify the question mark point as a triangle for which k. If k equals 1, then yes, it's a triangle. If k equals 3, no, but if k equals 5, then yes. What is a potential problem if k is even? There could be an equal number of nearest neighbors from both classes. You can't compute validation. Formula have to be adjusted. You can't find an even number. If k equals 2 and one neighbor is of class A and the other is class B, which one should the classifier choose? What would you expect to happen to the validation accuracy of a k-nearest neighbor classifier as k increases from 1 to infinity? Validation accuracy goes up and then down. As k increases, you begin to avoid overfitting and accuracy goes up. Once k gets too big, you begin to underfit and accuracy will go back down. True or false, k-nearest neighbors can work with data with 1,000 features. True. Can work with data with any number of features greater than 0. The .predict function in SciKit learns k-neighbor classifier. Class takes something as a parameter and returns something. So a list of points to classify and a list of predictions. A single point to classify a single prediction, a single training point, a single prediction. So it takes a list of points to classify and a list of predictions. The input needs to be a list even if it is only 1 point. What is the nearest neighbor to the point 1, 2? So -1, +1, 0, +1, 0, -2, +2, -1. So it'll be this. This between the points is 1, has the smallest distance. Overfitting happens when k is too big, so larger trends in the dataset aren't represented. K is too small, so larger trends in the data aren't represented. K is too small, so outliers dominate the result. This larger trends in the dataset aren't represented when k is too big. Oh, I see. How does k nearest neighbors define what it means for 2 points to be close to each other? By comparing the most important feature of each point, by using the distance formula, using all features of the data, by counting the number of features the 2 points share, by using the distance formula, using It's all features. Correct the distance formula with any number of features. Underfitting happens when k is too big, so outliers dominate the result. When k is too big, so larger trends in the data set aren't represented. Correct. If k is the size of your training set, then all predictors will be the exact same. Not terrible. Not terrible. So now they want me to build a cancer classifier, which I'm not going to make a joke about. I'm going to read normalization, and then I'm going to step away. Normalization. This article describes why normalization is necessary. It also demonstrates the pros and cons of min-max normalization and z-score normalization. Why normalize? Many machine learning algorithms attempt to find trends in the data by comparing features of data points. However, there is an issue when the features are on drastically different scales. For example, consider a data set of houses. Two potential features might be the number of rooms in the house and the total age of the house in years. A machine learning algorithm could try to predict which house would be best for you. However, when the algorithm compares data points, the feature with the larger scale will completely dominate the other. Take a look at the image below. So here, number of rooms doesn't matter nearly as much as years old. When the data looks squished like that, we know we have a problem. The machine learning algorithm should realize that there is a huge difference between a house with 2 rooms and a house with 20 rooms. But right now, because 2 houses can be 100 years apart, the difference in the number of rooms contributes less to the overall difference. As a more extreme example, imagine what the graph would look like if the x-axis was the cost of the house. The data would look even more squished. The difference in the number of rooms would be even less relevant because the cost of 2 houses could have a difference of thousands of dollars. The goal of normalization is to make every data point have the same scale, so each feature is equally important. The image below shows the same house data normalized using min-max normalization. Min-max normalization is one of the most common ways to normalize data. For every feature, the minimum value of that feature gets transformed into a 0, the maximum value gets transformed into a 1, and every other value gets transformed into a decimal between 0 and 1. For example, if the minimum value of a feature was 20 and the maximum value was 40, then 30 would be transformed to about 0.5. Since it is halfway between 20 and 40, the formula is as follows. The value minus the minimum over the maximum minus the minimum. Min-max normalization has one fairly significant downside. It does not handle outliers very well. For example, if you have 99 values between 0 and 40, and one value is 100, then the 99 values will all be transformed to a value between 0 and 0.4. That data is just as squished as before. Take a look at the image below to see an example of this. Boom, boom. Normalizing fixed the squishing problem on the y-axis, but the x-axis is still problematic. Now, if we were to compare these points, the y-axis would dominate. The y-axis can differ by 1, but the x-axis can only differ by 0.4. Z-score normalization. Z-score normalization is a strategy of normalizing data that avoids this outlier issue. The formula for a z-score normalization is shown below. Value equals mu over sigma. I believe that's sigma. Or maybe that's, I think that's sigma. Here, mu is the mean value of the feature and sigma is the standard deviation. I'm just gonna make sure that's right. Sigma, yeah. So back here, so mu is the mean value of the feature and sigma is the standard deviation of the feature. If a value is exactly equal to the mean of all the values of the feature, it will be normalized to 0. If it is below the mean, it will be a negative number, and if it is above the mean, it will be a positive number. The size of those negative and positive numbers is determined by the standard deviation of the original feature. If the unnormalized data had a large standard deviation, the normalized values will be closer to 0. Take a look at the graph below. This is the same data as before, but this time we're using z-score normalization. So squished and looking pretty good. While the data still looks squished, notice that the points are now on roughly the same scale for both features. Almost all points are between -2 and 2 on both the x-axis and y-axis. The only potential downside is that the features aren't on the exact same scale. With min-max normalization, we were guaranteed to reshape both of our features to be between 0 and 1. Using z-score normalization, the x-axis now has a range from about -1 to 1.5, while the y-axis has a range from about -2 to 2. This is certainly better than before. The x-axis, which previously had a range of 0 to 40, is no longer dominating the y-axis. Review. Normalizing your data is an essential part of machine learning. You might have an amazing data set with many great features, but if you forget to normalize, one of those features might completely dominate the others. It's like you're throwing away almost all of your information. Normalizing solves this problem. In this article, you learn the following techniques to normalize. Min-max normalization guarantees that all features will have the exact same scale, but does not handle outliers well. Z-score normalization handles outliers, but but it's now produced normalized data with the exact same result. Cool, 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 cool. And now next up is logistic regression.